Okay, so today I'd like to move into kind of a new topic. I'll start by talking about point estimation versus interval estimation. Okay, so point estimation is trying to provide someone with a single best guess of what they want to know. I've talked in examples of, I've given examples where we might want to know, for example, the average height of a population. And we can collect a sample. I've said that the sample mean is your best guess of the population average, at least your best single guess of the population average. Point estimation is about providing a single best guess, whereas interval estimation is about coming up with a range of likely values. Okay, so an example that I like to use is talking about like the due date of a baby. Okay, and did I give this example in class on Wednesday? Okay, so I've mentioned I have kids. I've got 3 kids. I remember going with my wife to all the pregnancy check-ins. And so my daughter has a birthday coming up, and so this is on my mind that, about 16 years ago, we were waiting for my daughter's arrival. The doctor had given her a due date of October 25th. Okay? So when a woman gets pregnant during the checkups, the doctor is very, always gives a due date for the baby, a best guess of when the baby's going to arrive. For my daughter, it was October 25th. Now, let me say, if I want to make plans in advance of the baby's birth, maybe grandma wants to come and witness the miracle of childbirth, okay? If my daughter's due date is October 25th, could I fly grandma down on the evening of the 24th? Go ahead and buy her a plane ticket months in advance on the 24th, so she'll be there when the baby arrives? That's kind of a risky strategy. Babies are very unpredictable, or at least, not perfectly born on their due dates. They might be born on their due dates on average, but knowing the due date itself doesn't help so much with planning as what my doctor told me next. My doctor said about half of babies are born within a week of their due date, and about 90% of babies are born within 2 weeks of their due date. Okay, so ranges of likely values. Yeah? So this actually helps a lot more with planning. If I buy grandma a plane ticket a week in advance, we know that there's only a 25% chance the baby will be born before that. If I buy grandma a plane ticket 2 weeks in advance, there's only half of a 10% chance, a 5% chance that grandma will miss the birth. Okay? So knowing a range of likely values helps more with planning in certain situations than knowing a point estimate. Okay? Right now, I guess the important statistic that I track daily are poll results for the upcoming presidential, gubernatorial, senatorial elections. Okay. And, I might have looked at the polls the other day and saw that the candidate I dislike has a 50.5% like popularity rating in the key swing state. Okay, we all know that Pennsylvania is going to decide the election, right? So I was looking the other day and saw that the candidate I dislike has a 50.5% chance of winning. I'm sorry, has popularity of 50.5% in Pennsylvania. So it looks like that candidate will win Pennsylvania, right? My single best guess is the candidate's going to win Pennsylvania. But does that mean I should go ahead and start, shopping for property in Canada, make plans to sell my house and move somewhere else based on this 50.5% that we're getting out of the polls? Well, maybe not. Right? Polls are not certain. Polls can be off by several percentage points, and it's very common that when you look at an opinion poll, it tells you there is a margin of error in this poll of plus or minus, and I'll name the margin of error. And that's stating that the pollster believes two things. One, they give you their best guess, but they acknowledge the actual value could be off, and there's a reasonably high chance that it is somewhere within a range. Okay, so an interval estimator gives a range of likely values plus a statement about how likely the range is, how likely the range contains the true value. Just as a note, often it's 95%. Okay, if it's not stated otherwise, it's usually a 95% margin of error. Okay, so let me talk about these interval estimates and how we construct them. Okay, let's go back to when we talked about X bar, or actually no, let me title this, that we want to construct a confidence interval. For, in this case, the mean, the population mean, which I call mu. Okay, what we established earlier is that if we conduct a survey, a random sample of n observations, and each value of xi has a mean of mu and standard deviation of sigma. Okay. Then x bar, which we calculate as 1 over n times the sum of the x values. Take all the x values, add them together, divide by the number of observations. That gives us our sample mean. Then x bar is a random variable. And the expected value of x bar is mu itself. Then, next thing we showed was true is that the variance in x bar is equal to sigma squared divided by n. And a third statement I made is that if x is normal, x bar is normal as well. Okay. Second, if n is large, then x bar is approximately normal. Okay, these are two justifications for saying we're going to treat x bar as if it's normal. Okay, x bar will be normal if x is normal, or it'll be at least approximately normal as long as we have a large sample. Okay, then this means that kind of according to the empirical rule, we had some statements like approximately 95% of, let me take this back, approximately 2/3 of x bars will be within one standard deviation of the mean. Okay, and a second statement was that approximately 95% within two standard deviations. Okay, in other words, what this is saying is that approximately 2/3 of the observations will be within, 2/3 of the values of x bar will, yeah.
What do you mean by normal in the statement?
When I say normal, I mean the normal distribution.
Okay.
So, yeah.
Okay.
Sorry if I needed to clarify. Yeah. So we'll use the normal distribution. Okay. Plus or minus 1 times, and then the standard deviation in x bar. So mu plus or minus, and variance in x bar is sigma squared over n, so the square root of that is sigma over the square root of n. The empirical rule tells us that approximately 95% will be within two standard deviations. So mu plus or minus 2 times sigma over the square root of n. Okay. So these are kind of quick ways of expressing a confidence interval. Okay, saying that like we're 2/3 confident that x will be within the range of mu plus or minus sigma over the square root of n. We're 95% confident that our x bar will be mu plus or minus 2 times sigma over the square root of n. Okay, so you get how these are sort of informal interval estimates? We're going to formalize this and talk about how to come up with your interval. And the numbers 1 and 2, we're not going to use those anymore. we're now going to consult the table for the standard normal distribution to get those kinds of values. Okay, so when we construct an interval estimate, one of the first things we do is state a confidence level. Okay, and usually we start by naming the tolerance for errors. In other words, the opposite of what we call confidence. So we might often construct confidence intervals for what I'll call alpha equals 0.10, alpha equals 0.05, or alpha equals 0.01. So this thing that looks like a kind of fish, this is an alpha, and it stands for the probability of error. Got it? Okay, so what we're talking about are often when we construct these confidence intervals, we allow a 10% or a 5% or a 1% chance of an error. Okay, why do we need to state this? Why can't we come up with a confidence interval that's perfect? Well, really, the only way to come up with like a 0 chance of error confidence interval is say anything is possible. Okay, so if my doctor really wanted to cover all her bases, like be exactly sure about when the baby is going to be born, the true answer is any time from tomorrow till, babies can be born more than a month after their due date. So, if the doctor wanted to be 100% correct, the only answer is the baby could come out at any time in the future. Okay, so we kind of need to narrow that down. And, the higher the tolerance for error, the narrower the range, right? If we want to be 50% correct about the baby's due date, we can pin it down to within a week. If we're allowing, only a 10% chance of error, then it's plus or minus 2 weeks of the due date, okay? The more certain the confidence interval gets, the wider it'll be. Same for polling, right? If I want to state with full confidence what will happen in the election, I am absolutely 100% confident that on election day, the percent of people who vote for the candidate I dislike in Pennsylvania will be somewhere between 0% and 100%. I can say that with complete confidence, but it's a useless prediction, right? If I wanted to narrow things down, I'm going to run some risk of error, okay? Maybe I could look at that one poll and say, well, it's going, like I can say with 99.9% confidence, it'll be somewhere between 30% and 70%. I can say with 90% confidence, it'll be somewhere between, and the range gets smaller. Okay, so if I want to have a lower risk of being wrong, then I'm going to come up with a larger range of possible values. Okay, so what this means is that we want to find, okay, so we name our tolerance for error, and then the confidence level is 1 minus alpha times 100%. Okay. In other words, these numbers that I wrote down, the confidence level when alpha is equal to 0.1, the confidence level is 90%. Alpha equals 0.05, we describe that as 95% confident. Alpha equals 0.01, we are 99% confident. Okay. So this is a matter of terminology. We'll use the term, like we'll say the phrase confidence level, like 95% confidence level, but often when we're doing the math, the important number is alpha, the opposite of the confidence level. Okay, 0.05 is the opposite of 95%. Okay, then we need to find the middle percent of the distribution. Okay, so this is like some homework questions that we did a couple weeks ago. Find the middle 90% of the distribution. Okay, those types of questions. Okay, so after looking at that table, we've actually got some z-values that we would use for these particular confidence levels. Z of 0.05 is equal to 1.65. Z of 0.025 is equal to 1.96. And Z of, we call this 0.005, is equal to 2.58. Okay. So those numbers will show up often in problems. You don't need to memorize them, but it might be worth memorizing them. You can always find them from the table. Okay, but again, as we often construct confidence levels or confidence intervals at one of these levels, it might be worth knowing what they are. Okay. So by the way, Z of 0.05 is equal to 1.65. What this really means is that the probability of getting a z-score greater than 1.65 is equal to 0.05. Okay, that's why we call it z of 0.05. Okay, then you have to remember also the probability that z is less than negative 1.65 is also 0.05. In other words, the probability that z is between negative 1.65 and positive 1.65 is 90%. Okay? And again, we call this number z of 0.05. That means there's a 5% chance of being larger than it. There's also a 5% chance of being smaller than negative z of 0.05. Okay, we would answer using this table for the standard normal distribution. So, like if we wanted to find the middle 90%, of the distribution, okay, let me give you all a tip for working with this table. Okay, if you want to find the middle X%, divide this number, 90%, by 2, and write that as a fraction. Okay, so half of 90% is 0.4500. That's the number we're looking for in the table, okay, if we're using this table. So we go and look in the table for the values that come as close as possible to 0.4500, and it's between 1.64 and 1.65. Okay, so let's call this number z of 0.05. I'm sorry. What we're looking for is something we call z of alpha over 2. So we call it z of 0.05. Okay. The 0.05 is what you add to the 45 to get a half. This is a value that has 5% of the distribution above it, and 5% of the distribution below negative z of alpha over 2. Okay, so in this case, we find that it is, I'll write 1.65, rounding to 1.65. Again, it's between these two values. Let me do another one. The middle 95% of the distribution. If we want to find the middle 95% of the distribution, we're looking for z of 0.05 over 2 is what, like, we're calling this z of 0.025. But my tip is look for half of 0.9500 in the table. Okay, so look for 0.4750 in the table. So we go look around our table and we see, right here. Our book has even highlighted that number or put a box around that number because it's important, like for constructing 95% confidence intervals. Okay, the number is, we read down to 1.9, and it's down from 06. So this value is 1.96. Okay, let me tie this to the empirical rule. The empirical rule says that approximately 95% of observations will be within 2 standard deviations of the mean. A more precise statement is that 95% of observations will be within 1.96 standard deviations of the mean. So this value, 1.96, is approximately 2. That's where the empirical rule comes from. Does that make sense? Okay. it comes exactly out of this table. And like the reason, I mean, honestly, a reason why people often do use 95% confidence is the convenience that it is so close to the value 2. It's just easy to do math using the number 2 instead of anything else. So like the very first person to sit down and think about constructing confidence intervals was a mathematician named Ronald Fisher. And he asked himself, like, how certain do I want to be with my predictions? And he said, well, I'm going to use 95% confidence for 2 reasons. One is I think 5% chance of error versus 95% chance of being right. That's sort of like pretty darn good. I'm correct most of the time, but it's not a range that's so large that it's useless. Okay, so he thought it was kind of a good compromise between being right and being wrong. But he also said, plus the math is really easy because it's so close to 2. Okay, let's do one other. Let's do, for the middle 99%. Okay, the z value that we're looking for is equal to what? Can you all do this? Okay. 2 point what? You're looking for the number, right. Look for 0.495 in the table. And what's the closest we come to that? I know it's hard to read here. 2.5. And then, yeah, okay, between 7 and 8. Okay. So we find z is equal to 2 point, and did I just say 5.8? Yeah. Okay. So let me go back to the previous slide. Now we have a more complete version of the empirical rule, basically. Any confidence level we want, we can find from the table. We're not restricted to simply 2/3 or 95% or nearly all. We can actually construct these confidence intervals for whatever we, for any confidence level we want. And a confidence interval for the mean will be confidence interval for, let me say, mu will be x bar plus or minus z of alpha over 2 times the standard deviation in x over the square root of n. If we use this formula to come up with a prediction of our, like to come up with a guess of the value of mu, it will be correct, like, or it will be wrong only alpha of the time. Okay. So in other words, suppose we know that IQ scores are normal with a mean of 100 and a standard deviation of 15. Then a 95% confidence interval for the mean is 100 plus or minus z of alpha over 2. Okay, we looked that up just a minute ago. For 95% confidence, that's 1.96 times the standard deviation over the square root of n, however many people we have in our sample. Okay. If we conduct a survey of 400 people, then what we expect is our confidence interval is 100 plus or minus 1.96 times 15 over the square root of 400. 100 plus or minus 1.96 times 15 over square root of 400 is 20. Okay. 100 plus or minus 1.96 times 0.75. Are you plugging this into your calculator?
Oh, no, I can't. I just did the first part, but...
This should be 100 plus or minus, and what is 3/4 of that is 1.5, I'm sorry, 1.447. Okay. So we expect we can be 95% confident that our sample mean is within 1.47 points of 100, right? So X bar between, okay, so probability that X bar is between 98.53 and 101.47. Okay, it's 0.95. Okay. So this range is our 95% confidence interval. So we say the 95% confidence interval is from 98.53 to 101.47. Okay. So this is our standard version of a interval estimate. A confidence interval, we state a range of likely values and how likely it is that the range contains the true value. So we're 95% certain that this range will contain the correct value. Okay, now, got it? So let me do the confidence interval for a proportion. Okay. Remember the setup. We conduct a survey of N people from a population with the proportion P. Okay, P is the proportion of people who have some characteristic in the sample X have the characteristic. Okay, then we calculate P hat equals X over N is the sample proportion. Okay. I said a few things about the distribution of P hat. First, the expected value of P hat is equal to P. Second, the variance in P hat is P times 1 minus P over N, number of observations. The third statement I'll make is that P hat is approximately normal. In other words, it approximately has the normal distribution if N is large. Okay. So the way we construct confidence intervals is more or less the same. It's going to be the estimator plus or minus z of alpha over 2 times the standard deviation in the estimator. So a confidence interval looks like, and then it's P plus or minus, or let me say P hat plus or minus z of alpha over 2 times the standard deviation in P hat. Okay. P hat plus or minus z of alpha over 2, and then we substitute the formula for the variance in P hat. So this is P times 1 minus P over N. Okay. So let's do an easy example. Suppose P is equal to 0.5 and N is equal to 400. What is a 90% confidence interval for P? Well, we expect that 90% of observations will be in the range of p plus or minus, and the number that we call z of 0.05, right? 90% confidence, so we're talking about a 10% chance of error. We're going to look up z that has 5% of the distribution above it, times the square root of p times 1 minus p over n. Okay. 0.5 is the value of p, plus or minus. And we looked this up a few minutes ago. For 90% confidence, the z value that we use is 1.65 times, and then it's the square root of 0.5 times 1 minus 0.5 over n, 400. Okay, so 0.50 plus or minus 1.65 times, and then we have 0.5 times 0.5, that's a quarter, divided by, okay, so it's 0.25 over 100, over 400. And you put it all in. Okay. 0.50 plus or minus 1.65 times, and I know this is, let's see, 1 over 40, 0.025. Let's see. Evaluate what's inside the or inside the square root. Thank you. 0.025 is the square root of that?
Yeah.
Yeah, okay. 0.025. Okay, so it's 0.50 plus or minus, okay, 1.65 times 0.025 is?
The final answer I got 0.04125.
0.04125. Okay, that sounds good to me. Okay, in other words, from about 0.45875 to 0.54125. Okay, so get this. When we conduct this survey, 90% of the time we expect that we're going to get a value between basically 46% and 54%. Right? So we have expressed right here our margin of error. In other words, for this particular poll, there is a 4.125% margin of error when we're using 90% confidence. And this is something to keep in mind as you all interpret opinion polls. They are not going to be exactly correct. they'll be off by a few percentage points. We can actually do a calculation of how far off we expect the estimates to be. Okay, we're 90% confident that the actual value will be within 4.125 percentage points of our estimate. Okay, does that make sense? Okay. And by the way, like this number, like this size poll is pretty big, isn't it? Right, 400 people, you're surveying them for their preferences. You see there's actually a pretty wide range of what you could get. Like there's, you could be off by several percentage points. Okay. Any other questions about this? I want to do one more example, maybe. Okay. Suppose we survey N equals 900 people, and we find P hat equals 0.64. Okay, so in our sample, 64% of people say that they will vote for this candidate. Okay, let's construct a 95% confidence interval. Okay, basically we know our point estimate is 0.64. The thing that we really need to find is the margin of error. Okay, so it's going to be 0.64 plus or minus our margin of error. And so we're going to be calculating that. 0.64 plus or minus z of alpha over 2 times the square root of, we'll use p hat times 1 minus p hat over n. Okay. Can you all do this? Okay, so we looked up one of the important things in the table just a minute ago, and it's this z value, 1.96, okay, and then plug in for p hat, right? We keep our p hat is equal to 0.64, 1 minus p hat, 1 minus 0.64, okay, divided by 900. Okay, so plus or minus 1.96 times the square root of, this is going to be 0.8 times 0.6, it's 0.48 over 30. So plus or minus 1.96 times, what is 0.48 over 30? Or, well, what is the number after you evaluate the square root? 0.016? Okay. So in other words, plus or minus, and what is 1.96 times 0.016? 0.031. Okay, 36. I'll just, okay. 0.0314. Okay, so we now know our confidence interval is, or let me say, we now know our margin of error. The margin of error is plus or minus 0.0314, or as people say in percentage form, 3.14 percentage points. Okay, so a 95% confidence interval is, and I'll say 0.64 plus or minus 0.0314. Again, like for people who like percentage numbers, 64% plus or minus 3.14 percentage points. Does that make sense? Okay. This is real stuff. This is exactly what you all see in the polls. This is how it's done. All right.
And like, how does it matter? Because 3% in the polls is a lot.
If 3% in the polls is a lot, yeah. I mean, a sample size this big, even, you've got a pretty substantial margin of error. 900 is actually close to the sample size that many pollsters use. I mean, if you look at, I'll say, the website I really like is called 538.com. Is a website that, that aggregates poll results. And you'll see that like a common poll size is probably between about 500 and 1,000 people when they're conducting these surveys. And so the margins of error are several percentage points. So, you know, you look at whatever outcome there is, like whatever we're looking at in, say, Pennsylvania, and I picked on Pennsylvania and like talk about the candidate I don't like. I'm honestly not picking favorites in class. I hope you all get that. So the polls in Pennsylvania are virtually tied. You'll see one poll that puts Harris a point or two ahead. The next poll puts Trump a point or two ahead. They bounce around by a couple percentage points from one poll to another. We have a formula now for knowing that's kind of normal. That's typical. We expect a range of about plus or minus 3 percentage points, even with a sample this big. Yeah.
So when these like polls are like tampered with, when they talk about the factor of safety was tampered with.
When people talk about polls being tampered with.
Yeah, because like I feel like if 64% like vote for somebody, it's kind of a set. But if the factor of safety is the margin of error is so big, then that can be messed with.
Yeah, with the margin of error so big, I think this is why, like, you'll hear kind of poll results maybe being distorted, and one side will read a lot into the fact that like we're ahead by 1 percentage point according to the last poll, and the pollsters will say no, you're tied according to the poll. Like you're within the margin of error. There's no reason for us to confidently say one person is ahead or the other person is ahead.